Okay, so let's start our last lecture. And I guess you probably know the stuff very well, so the attendance is a record low, but never mind. Okay, so we are going to continue the examples of the last year paper, the last semester exam paper. Okay, so please be alert because I realize when I try to solve them, it's so easy to make mistakes. So please be alert. There are lots of mistakes inside, probably. Okay, so. Okay, so the first 11 questions was done on Tuesday, right? So now we continue from question 12. Okay, so actually question 12, 13, and 14 are talking about the same thing. So this is part of the topic in fair division, right? So we learn there's a method called sealed bids. Right? So the scenario in these problems are there are three people, A, B, C. They want to divide an estate consisting of a house, a car, and some collection of coins. Right? And then the value in based on their own view are listed in this table. Right? So the bids for the items in units of $1,000 are listed in the table below. Right? So in the eyes of A, the house is worth 180,000, and so on and so forth. Right? So now we are going to apply this method of sealed bids to give them a fair division. We want to divide these things fairly, and so we'll see what happens. Okay? So question 12 says this. So we are going to follow the algorithm, okay, based on this data. So after the initial allocation, Mr. C needs to pay the estate this amount, and A needs to receive this amount from the estate. So is this true? Do you have an answer? You have done this, right? Is this true? True, right? Okay, so let's see. So the next slide. Okay, so here, this is according to the algorithm, we are going to do this. So first, for each item here, we look at the highest bidder, right? So, for example, for the house, Mr. C he is willing to pay the highest price. So we are going to give the house to him. Right? So the red letter, the highlight letter says, indicate the item goes to the guy who make the highest bid. So C gets a house, A gets car because the 12 is highest bid, and B gets the coins. Okay. Then after that, we calculate the total bids for each person. So you add the numbers up, you get these things. And then divided by 3. So these are the fair share based on their evaluation. Okay, so hopefully the numbers are correct. So you get these are the fair shares. Now, for Mr. A, he think he'll get 65, right? But he already got a car. And in his eyes, the car was 12. So the state still own him 53, right? So the number 53 comes from 65 minus 12. And similarly for B is 75 minus 5. For C is 76 minus this. But this is an active number, means C owns the state this amount. Okay, so these all from the algorithm. And so therefore, it is true, right? So in the estate will pay Mr. A this amount in thousand, and C will pay the estate this amount in thousand. Right? Is this right? Okay, so C needs to pay the estate this amount, and A needs to receive this amount. So it is correct, right? So the answer is correct for 12. Now let's see next question. It's all related. So after everyone gets their fair share, there's a surplus of this amount in the state. Is this true? Okay, so it's true because if you calculate the estate receives from C this amount, right? And the estate pays 53,000 to A and 70,000 to B. So there's a surplus which is 21,000. Okay, so it is correct. There's a surplus of this in the estate, and then we are going to divide. So sorry, the uploaded the solution had an error, right? So each person, so the 3 person will share the surplus. So each person will get 7,000 extra. Okay. So then the next question, question 14 says, in the final allocation, B gets the coin collection and $80,000. So the answer is no, it's not true, right? So it's false. Well, it is correct that B gets a coin, right? Because he made the highest bid, but he also gets 70,000. Sorry, the old number was wrong. So he'll get 1/3 of the surplus, which is 7,000. So he gets 77,000, right? So besides a coin, the number 80 is not correct. Okay, so there's a correction of the. So be alert. I made many mistakes like this. So okay. All right. So that's the question about the fair division. Okay. Now let's move on to the next few questions, which are combinatorics. Right. So since the question has to be in true or false, so therefore the question is a little bit artificial. Otherwise, it would be more natural. Okay, so let's see. So question 15. So there are more ways to arrange 4 identical red balls and 4 distinct persons in a row than to distribute 9 identical balls in 5 distinct boxes. Well, okay, so we have to compare 2 numbers, right? After the comparison, we decide which one is larger, right? And okay, it's an artificial example, right? Who is going to arrange identical balls with distinct persons in a line? I mean, in real life, probably we never do this, but so let's see. Okay, so well, we'll do the calculation and compare the number. If it's right, then it's right. Okay. So let's first calculate the number of ways to arrange the balls, 4 identical balls and 4 distinct persons in a row. Right? You may have your own ways to do. There are many different ways to do calculation. So what I'm going to do is this: if we temporarily assume the balls, the red balls are distinct, and then there are 8 factorial many ways to arrange them on a line, right? But the balls are identical, so therefore there are 4 factorial arrangement. Actually, they are the same. So you have to divide 4 factorial. So the total number of ways for the first item is 8 factorial divided by 4 factorial, right? So if the calculation is correct, you get 1,680. Do you get this? Okay. Now let's look at the other part. So we want to distribute 9 identical balls in 5 distinct boxes. So we have done this before, right? So the idea is we think of, we have 4 dividers to create 5 boxes, right? You can think of the red balls as digit 0. Then you have 4 dividers, which are digit 1. So the way to distribute 9 identical balls in 5 distinct boxes is the same as distributing. You have a string of 0 and 1s. You have 10 zeros and, is it 10 zeros? You have 9 zeros and 4 1s, right? So this arrangement is equal to the number of ways to put 13 digits. Among them, there are 4 1s, right? So it's 13 choose 4, right? So if you calculate this number, you'll get 715. So the first one is bigger, right? So there are more ways to arrange this than that. Correct? Correct? Okay, good. Okay, another combinatorial. So again, we are comparing 2 numbers. So there are more ways to arrange 7 persons at a round table with 10 seats than to arrange 5 identical red balls, 5 identical blue balls, and 3 identical green balls in a line. Again, we calculate the number of the 2 items and then compare them, right? So, well, let's first do the calculation. So again, we have learned how to arrange people on a circle, right? So we have 7 persons. Suppose the seats, right? So in the lecture, the solution is, imagine there are 3 ghosts, distinct ghosts, occupying the empty seats, right? So you have 10 distinct persons. So then the total number is 9 factorial because it's circular. So you have to identify 10 of them as 1, right? So you have 10 factorial many ways to arrange the person and the ghost, right? Now suddenly the ghosts are the same. So the arrangement of ghosts are all equal, create the same thing. So you have to divide the 3 factorial, which are the possible arrangement of the ghost, the empty seats. So the total number is 9 factorial divided by 3 factorial. Again, so we get this number. Now, what about the other one? So the other one, there are several ways of doing it, right? I think the simplest way is this, right? So altogether we have, we have 5 identical red balls, 5 blue balls, and 3 green balls. So we have 13 balls. So suppose they are all different, and then the way to arrange them is 13 factorial. Now, the red balls, we have to identify them. So if you want to get rid of the repetition, you have to divide 5 factorial. And then for the blue balls, again, you should identify the permutation with the blue balls. So you have to divide another 5 factorial and another 3 factorial for the green balls, right? So you get this, right? Or you can think of, you can do this. You can think of the arrangement are done in 2 steps. The first step, you arrange the red balls and the blue balls. So it's like you have a string of 0 and 1s, and total length is 10. Among the 10, there are 5 1s, right? Then after that, you can shuffle in the green balls. So the situation is like, so for each arrangement of this, you shuffle in the 3 balls. So you get, it's like 13 choose 3, right? So there are 13 positions, you can choose 3, which are the green balls. If you do this, it's exactly the same. So the answer is this, okay, 72,072. So which one is bigger? The second one is bigger, right? So So the claim of this is false. Is this correct? So, be alert. I often make mistakes, but okay. So, but if you say it's correct, then it's correct. All right. So these are the combinatorials. The next question, two questions are about transportation. We didn't cover. Okay. So now we move on to graph theory. So this is about Euler circuit. Right? So the following graph can be Eulerized by adding 4 edges. We didn't use the word Eulerized. Right? So the meaning of this is after adding the 4 edges, we have an Euler circuit. We have a closed Euler work. Okay? Is this true? So we learn the theorem by Euler, which counts the number of odd degree vertices, right? So if you have, in order to have an Euler circuit, every vertex must have even degree, right? So now let's look at this. So let's look at them line by line, right? Let's count how many odd degree vertices are there. Okay, this part, no, this is even. This is 1, right? 1. This is, so the other 3 are even, right? So 1, 2, 3, 4, 5, 6, 7, 8, 8. So we have 8 odd vertices, okay? So can we kill them? So the idea is to pair them up and then use an edge to connect the pair so that the degree become even, right? So, so we have 4 pair of vertices. You can use 4 edges to connect them, right? So the answer is true, right? The connection, there are many ways of doing it, right? So you can do it by just arbitrary connection. Questions? Is this okay? So the answer is yes, so you can do this. Okay. Now, the next one is about chromatic number. So we have this graph, right? So let me remind you what is chromatic number. So we want to color the vertices, right? So the rule says you cannot color adjacent vertices using the same color, right? So therefore, we want to figure out what is the minimum such coloring, right? So such coloring is called a proper vertex coloring. So we want to find the minimum number used in a proper vertex coloring, okay? So, so the question claims that we can do this using 4 colors. Okay? What do you think? Is correct? Yes. Okay. So there are two okay, so correct, this is true. So there are 2 aspects, right? So first, we cannot use less. Secondly, we can use 4. 4 is okay. So why can't we use 3? Right? So in the lecture, we say if a graph contains a complete graph with, say, K4, right, with 4 vertices, then you need at least 4. There's no hope to use 3. So this graph actually have 2 copies of K4, right? For example, this is a K4, right? Somehow the PDF annotator doesn't work today, so I have to use this. Okay, so these 4 will give you a K4. The other 4 also give you a K4. But never mind. As long as it contains 1 K4, the chromatic number is at least 4. Okay. Now, can we use 4 to color it? Well, let's try, right? So let's just say, look at this K4. Use 4 colors. 1, 2, 3, 4. Right? So 1, 2, 3, 4. Now for these, for the second K4 here, I have 1, 2, and 4, right? 1, 2. Okay, so let's try again. 1, 2. Suppose it is 1, 2, 3, 4, right? Suppose we do this. Then the rightmost vertex is adjacent to 1, 2, and 4. So we have to color him by 3. So we have 3, 4, 3 here. And then you can color this by either 1 or 2. Or you can even color it by 4. Right? So you can do it by 4 colors. So therefore, the chromatic number is indeed 4. Okay, so I think this is easier than the earlier ones. Okay? Okay, so we move on really quick. So we move on to number theory. The claim is the remainder when 5 to this power and plus 2 is divided by 11, the remainder is 7. Okay? So we want to find the remainder. Okay, so let's see. Let's do the calculation. So we can use Fermat's-Little theorem, right? So 5 does not divide 11. 11 is a prime. So 5 to the, a to the p minus 1 is congruent to 1 modulo p, right? So apply to a equal 5, p equal 11. So we get 5 to the power of 10 is congruent to 1 modulo 11. So therefore, this 5 to the 231 is congruent to, you write this as a multiple of 10 and with the extra 1. So this is equal 5. Right? Now we have extra 2 here. So if you add the 2, you get 7. Right? So the result is correct. Is this okay? Okay, good. Okay, so then change topic again. So we look at, this is, when we talk about probability, we had one application called false positives, right? So you're going to, suppose you go to a hospital, you do some test. Well, the test usually is effective, but sometimes it gives you some false result, right? So suppose you don't have this disease because of the error that the test will say you have, so it's called false positive. Now we have seen examples like this, right? So let me read the news story, but the mathematics behind them are the same as we learn. Okay, so the story is this. A test is for the performance-enhancing drug, right? So it has 95% success rate on cheating athletes who use the drug. Right? On the cheaters, if they go through the test, 95% of them get caught. Okay? But it has a chance of 3% to give false positive, right? So as I just said, the false positive means the people are innocent, but somehow the test shows positive. Okay? So the figure was 3%. Now, if 1% of all athletes are cheating, and John tests positive for the drug, then the probability of John being a cheater is between certain numbers. Right? So this is the storyline. We want to figure out, suppose a person was tested positive. Now, what is the percent he is a cheater? Okay, so, well, let's do the calculation and see. So first we have to translate the storyline into the language of probability, right? So we have done this before, so let's see. So let A and B be the events of cheating athletes. Okay, so A is the collection of events that people are cheating. Okay, and B is a collection of events that the testing is positive. Okay, so we need to calculate the conditional probability under the condition B, right? Suppose the test is positive, what is the probability of cheating happens? So this is a conditional probability, right? So suppose the test is positive, what is the chance of the person, Mr. Zhang, is being a cheat, right? So we want to calculate this conditional probability, right? So this is the real target. So let me remind you how to calculate, or this is the definition of conditional probability. So this is, we shrink the sample space to B, and then we look at the probability of A intersect B, right? So it's P of A intersect B divided by P of B, okay? So now we have to figure out, based on the data we are given, what is the probability of A intersect B and what is the probability of B, okay? Okay, so the probability of A intersect B, A is cheating, B is testing positive, right? So we know that there are 1% of people cheating. And among the 1%, the people cheating, there's 95% to catch. So the probability of A intersect B is the product of the two. Okay, so it's this number. Okay. Now for probability of B, from the data we cannot get it directly, but we can only get it indirectly. So we use the property that, okay, P of B, the probability of B is P of A intersect B plus P of A complement intersect B, right? So we use the property of sets, right? So you know that so you know B is equal to A intersect B union A complement intersect B. So therefore, the probability of B is probability of A intersect B plus probability of A complement intersect B. We have calculated A intersect B, P of A intersect B, which is this number, 0.0095. We have to calculate the probability of A complement intersect B. So in other words, A complement are the innocent people, right? So what is the probability of the innocent people who get positive? So there are 99% of them are innocent, but there's 3% giving false positive, right? So it's this number. So you add them up, you get this. So the conditional probability, if my calculation is right, is this, is between 24 and 25. So the answer is true, right? Is this okay? Okay. Okay, let's move on. So then we move on to a game theory. Now, in the lecture notes, we use tennis, right? But this problem now, we try to use soccer. Okay, so the next three questions, actually only two are covered in our syllabus. So we look at next two questions. So concern the following payoff matrix for a football game, soccer game. So we have this payoff. I guess I don't need to explain the payoff matrix. So we have this payoff matrix. So we have two teams. So these are Liverpool and Manchester City. You can change it to other teams, right, if you want. Okay, so each team have two so-called strategies. So for example, Man City can choose attack or defend. The same for Liverpool. Right? Liverpool can choose attack or defend. So for a profile, okay, so suppose both of them choose attack, right? This table says Man City will have an advantage. Man City will get 9, and Liverpool will score 1, right? So the payoff is we pay. In this case, Man City will get 9 and Liverpool will get 1. The same for the others. Okay. Now, what is the question? So the question is, first, there is no Nash equilibrium in pure strategies, right? But there is a Nash equilibrium in mixed strategies. And with Liverpool adopting the strategy to attack with probability 0.6. Okay, so there are several things, right? So first, is this correct? There's no Nash equilibrium in pure strategies. Well, the answer is, so this first sentence is correct because there's no dominant strategy at all, right? So if you look at the numbers, there's no Nash equilibrium. So the first part is correct. But there is a Nash equilibrium in mixed strategies. This is also correct, right? Because we know that in finite games, there's always Nash equilibrium in mixed strategies. Now, the only thing left is this number correct? Is the number 0.6 correct? So it turns out this is wrong, I guess. So let's do the calculation. So if this number is wrong, then it's false, right? So here it says the first two partial statements are correct. So now the devil is in the details, right, to see whether this is 0.6 of attacking. Okay, so let's do the calculation. So we are looking at things from Liverpool point of view. So he can choose attack with probability Q, and then he'll choose defend with probability 1 minus Q, right? So now we calculate the payoff of Liverpool, right? So he is going to do the following analysis. So suppose Man City attacks, right? And then what is the payoff? If Man City attacks, we look at the first row of the table. So Liverpool will get 1 with probability Q, right? So this is 1 times Q. And he'll get 8 with probability 1 minus Q, right? So the expected payoff for this situation is Q plus 8 times 1 minus Q is 8 minus 7Q. Okay. Now suppose Man City choose the defense to play the second strategy. The Liverpool's expected payoff, okay, so with probability Q, he gets 7. So it's 7Q, and plus 4 times 1 minus Q. So it's 4 plus 3Q. Okay, so these are the expected payoff, right? So then you can draw the line and analyze his best payoff is at the intersection of the two lines, right? So here I don't want to repeat the whole process. I'll say equate and solve. So you equate the two equations and find where Q is. So it turns out to be Q is at 0.4. And this 0.4 is really for the probability of attacking. It's not for the defending, right? Because if 0.4 is for attacking, the defending is for 0.6. So, sorry. So at the Nash equilibrium, Liverpool has to choose attacking with the probabilities 0.4. But the question says 0.6, so it's wrong. Is this okay? Okay. Okay, then the next question is the expected payoff for Man City at a mixed strategy Nash equilibrium is 4.8. So now we shift the point of view from Liverpool to Man City, right? So we are going to do more or less the same calculation and then find out what is the probability P Man City should use at the equilibrium, and then calculate the payoff, right? Okay, so we use the same thing. Okay, so let's see. So from Man City point of view, he is going to analyze what happened to Liverpool, right? So if Liverpool attacks, we'll look at the first column. So the expected payoff is, okay, if we look at the first column with probability P, Man City get 9, right? So it's 9 times P plus with probability 1 minus P, you get 3. So 3 times 1 minus P. So it's this number. Okay. Now, if Liverpool defend, and Man City's expected payoff is, okay, we look at this column and the first component, right? So it's with probability P, you get 2. So it's 2P plus 6 times 1 minus P. So it's this number. Again, you have to equate these two numbers so that you find the equilibrium. So you get P is 0.3, and you plug in 0.3 in either of these equations, you get the corresponding payoff. It turns out to be 4.8, right? So here you get 1.8. So 3 plus 1.8 is 4.8. So the answer is true. Is this okay? Okay. So the next question is beyond our syllabus, so I will not do it. Then we move on to coding. So we look at ISBN number. So these 10 digits supposedly to be an ISBN number. Okay. So we want to find out what is the n. So is n is 4 or something? Okay. Okay. So let's work it out. Okay. So we learned last week that ISBN number is how do we get ISBN number? So we want to add extra bit for correction, right? So that the weighted sum of these is congruent to 0 modulo 11. Is 11 divide the weighted sum, right? So what is the weighted sum? So you have 10 digits here, including the extra bit, right? You have 10 digits here. So the first bit you give weight 10. The second bit you give weight 9, and so on and so forth, right? So you calculate weighted sum. So in our case, it's 10 times 0 plus 9 times 2 plus 8 times 3, and so on and so forth. So you write down these expression, then calculate the weighted sum. If my calculation is right, it turns out to be 6n plus 107. Okay? Now, if this is a correct ISBN number, 11 should divide this. Right? So it should be congruent to 0 modulo 11. Okay. So now is it true? If I plug in n equal 4 here, so I get 24, right? So I get 131. That is not a multiple 11, right? So the statement was wrong. Now, what is the correct number? Well, we can easily calculate. Actually, 6 is the correct number. When you plug in 6, you get multiple 11, 143, right? So, okay, so it's quite easy. And then we we have another interesting method of coding, right? So this is Hamming 7-4 code. Right? So suppose you receive a message like this, right? So it's a 7-digit message, but there are some corrupt bits, right? So the 4s and the 6 are unknown, right? So, but we design Hamming code so that we can, if we are lucky, we can recover the bits, right? So the the claim is if you receive this one with 2 corrupt bits, then you can still decode you can still recover the original transmitted words is this. Okay, so let's figure out what are the bits. Okay, so the Hamming code, right? It's easier to draw the circles, right? You can solve congruence equations, but that's not very intuitive. So the easiest way is to draw circles like this, and fill in the 7 bits in this way, right? The first bit, second bit, third bit, fourth bit, fifth, sixth, seventh, right? So you fill in the bits according to the rule, right? Now, the Hamming code, when you design it, in every circle, in A or B or C, the total number is even. Or you can say number of ones is even, right? So let's see. So in this case, if you look at circle A, right, you can solve x equals 0, right? Because to make the total number of ones in A is even, x has to be 0. So if x is 0, then y has to be 1, right? So in other words, the fourth digit is 0, the sixth digit is 1. But this is wrong, right? So the correct words should be this. Okay, so so the answer is false, and you get this. Is this correct? You agree? Okay, good. So we are moving quite fast. Okay, so the last 3 questions is about, go back to probability, is about expectation. Okay, and with some combinatorics. Okay, so let's try. So they all talk about the following situation. So you're offered the chance to play the following 2 games. So game A says you pay $1 to play, and then you pick 2 balls from a box containing 4 red balls and 3 blue balls. If you get 2 balls of the same color, you win $3. Otherwise, you get nothing, meaning you lose $1. Okay. Because you paid $1 to. Okay, so the game B says you pay $2 to play the game, and you pick 2 balls from, it's almost similar, right? You pick 2 balls from a box containing 3 red balls and 5 blue balls. If you select 2 balls of the same color, if you draw the 2 balls from the same color, then you win $5. Otherwise, you get nothing. Okay. So you're offered to play the 2 games. So the question is, the probability of drawing 2 balls of the same color in game A is at least as large as the probability of drawing 2 balls of the same color in B. So first we calculate the probability. Okay. So then we compare the probability, and we know whether this is true or false. Okay, so let's do the calculation. So let's look at what happened in game A, right? So in game A, you draw 2 balls from 7 balls, right? So the box contains 4 red and 3 blue. So total number is 7. So you draw 2 out of 7, right? So it's C of 7 choose 2, right? Now, you want to calculate probability. So you want to calculate what is the chance you get the 2 balls of same color. So it's either blue or red. Is it red or blue? Yes, red or blue, right? So the chances to get red, 2 red, is 4 choose 2. The chance of getting 2 blue is 3 choose 2, right? So altogether, you have this chance. They are destroyed, right? So the chance is this. So therefore, the probability is 3 over 7 after you simplify. Is this okay? Is it correct? Okay. Now, do the same calculation as in B, right? So you have total 8 balls, and then 5 of them are maybe red and 3 of them are blue. So you do the same calculation, you get 13 over 28. Now, which one is bigger? So the B is bigger, right? So the answer, what's the question? The question says A is at least as large, but A is actually strictly smaller. So the answer is false. Is this okay? Okay, so then question 29 says the expected winning for game A is less than that of game B. So then we have to calculate the expected winning. Right? So the expected winning for A is, so the expectation is, for a random variable is, so it's the sum of k times the probability of x equal k, right? So here you get $3 times the chance you get $3. So in other words, the chance of drawing the same color balls, right? And you have to minus 1 because you paid $1 for the game, right? So the expectation is this, okay? So we just calculated the probability of winning in A, right? So that's 3 over 7, right? So you get 9 over 7 minus 1, so it's 2 over 7. Okay. Similarly, for B is the chance you get the payoff 5, which is 5 times the chance you get that. But you paid $2 in game B, so you have to minus 2. So if you do the calculation, you get 9 over 28. Now, which one is bigger? So the first one, okay, is smaller than the second one. Is it true? The expected is less than. Okay, so this is true, right? Okay, good. So last question. So suppose you pick to play game A with probability 1/3 and game B with probability 2/3, right? So, and repeat this. So because when you do expectation, this is, you only see the result in the long run, right? For a single game, it doesn't mean anything. So you have to use law of large numbers, whatever. So in the long run, things behave like the expected number. Okay, so that's why the scenario says you have to repeat this for many consecutive days and years or whatever. So in the long run, your expected winning is not as good as if you just choose play game A repeatedly. So in other words, if you look at the expectation of this mixture, and then you have to compare with expectation of just play A, right? So, okay. So we know the expectation of just play A. This is 2 over 7. Now, what is the expected payoff for the mixture? So you play 1/3 with probability 1/3, you get this payoff, right? It's 1/3 times E of the expectation of A, plus 2/3 times E of expectation of B, right? So the calculation gave me this 13 over 42. Right? Now you have to compare with, if you just play A repeatedly, you get 12 over 42. So the mixture is give you better return, right? So it's not as so this is better. It's not only as good as, actually it's better, right? So the answer is this one is false. Okay, is this right? Do you agree? Okay, good. So with this, we end everything, right? So next Tuesday, I will be here, and I'll treat the lecture hour as consultation. And I received some emails. People send me the sample of even, how to say, the previous exam papers, not only from last semester, but from earlier years. Okay, so if you have specific concerns, you have to email me. So I will answer those questions to you. But as you know, every semester the lecture is different, the topics are different, and the problem format are different, right? For example, maybe they will ask you to prove something. So I don't know. If you have any concerns, just tell me the question number, so I have to prepare, and then we can talk next Tuesday. So otherwise, well, I'll see you in the exam. Okay. All right. Okay. Thanks for coming. That's it.